my name is Guillermo and I'm part of the research team here at Bechtel. Part of our mission at Bechtel, we strive for continuous improvement, and we do this by identifying and analyzing project flaws so that we may improve our abilities to carry out future projects. This presentation will go through a particular study conducted by a project team, and at the end, we'll cover potential ideas for future improvement. The study took place at the construction site of a future home in Pennsylvania. The activity observed was the installation of precast foundation walls. During the observations, crew balance and process charts were created to help find areas in need of improvement. The study will also cover the problems that were identified in the construction activities, including excess idle time, poor equipment choices, a lack of safety precautions. After that, we will go through proposals that were made for possible improvement. The proposals will go through ways in which cycle time can be reduced, the number of workers can be reduced, and how to make better decisions regarding equipment needed on the site. Overall, this will save a lot of time and money in all future projects.
Methods of study that we used. One is a flow diagram, which allows engineers to visualize the workflow on the job site in order to identify inefficiencies and make changes if possible. The flow diagram follows the steps of an activity chronologically and shows the movement of people or things. A process chart typically accompanies the flow diagram and lists all the steps in a construction activity. There are 5 symbols that are frequently used in a process chart, but the circle and the triangle are generally the most important activities. The circle stands for a do operation, which includes both essential productive work and contributory non-productive work. Transport operations are required in almost every construction activity since material has to be moved around the job site in order to ensure easy access while in use. The flow diagram method. It is created by keeping track of what each machine and person is doing and for how long over a period of time. This chart can make any unproductive time easy to spot. It is possible to see if any of these non-effective moments are isolated or if they are caused by other problems in the work cycle. The main limitation of the crew balance chart, however, is that it does not necessarily show the efficiency of each member while working, since being busy doesn't necessarily mean the best use of time and the best method. Work pace is also not reflected well in the diagram. Despite this, it is a useful tool in finding generally where time and resources are being wasted.
And I'm part of the research team here at Bechtel, and I will be going through the analysis of existing operations and problems. In order to create the flow diagram and process chart, the process of installing the basement wall was closely monitored to determine the various points of interest and the different steps involved in this particular construction activity. This figure is an example of a flow diagram and process chart created for the construction activity observed in the video. The various steps in the process of installing the basement walls are detailed in the flow diagram and process chart. Since there was no way to measure the distances required for the material and items to be transported, an estimate had to be made. In this case, we estimated that the basement walls had to be transported approximately 35 feet through an arc due to the swing of the crane. The anchoring materials, for example, the nuts, bolts, and the sill plate, will have to be transported at approximately 5 to 10 feet from the newly placed wall segments. The crew balance chart captures the last 2 cycles of placing the foundation wall and sometime past toward the end of the workday. A period of 30 minutes was observed in 30-second intervals. By observing the chart, we can see that the cycle generally consists of the crane loading the wall segment and moving it into place with the workers guiding it. Then the 3 laborers worked at the same time, with one making sure that the segments were level and plumb with each other and bolting it into place at the top. Another bolting the segments together at the bottom of the wall, and the last laborer caulking the creases on the outside. Cycle times are not very reliable for this particular chart because the crew has to readjust the wall segment after placing it, and because wall segments are placed at different positions on the job site. However, we can easily see the inefficiency of the work time. There's a significant amount of idle time from all workers and the foreman, which is shown in orange on the crew balance chart. Some of the idle time is built in due to the cycle time of the crane, but there's a lot of room for improvement for overall productivity and in the overall cycle. These potential improvements and unproductivity will be discussed later.
Speaking about our first proposal for our term project, we are recommending the foreman use his time on the construction site more effectively. His idle time is 100%. From the knowledge of our productivity class, we have an understanding of how the foreman has an ample amount of idle time because he is busy observing the work actions of all the workers. But we believe the foreman can cut his idle time in half by assisting the 3 other workers. If we analyze the crew balance chart, the foreman can assist the workers in a couple different areas to decrease his idle time. For example, from minute 6 to minute 10, all 3 workers are guiding the foundation walls. The foreman can assist in the work and reduce the overall time it takes all 3 workers to complete the task. This will automatically improve the production rate of all the work crew. In addition, from the video, we believe that the foreman can be more attentive to the work being completed on the job site. Several times he walks away from the site and also spends an ample amount of time on his phone away from the site.
Hi, my name is Meng Wang and I'll talk about Proposal 2. Our second proposal also increases productivity, but does not reduce cycle time. It is a proposal to reduce the crew on site. The main factor affecting such a decision is the amount of time available to finish the project. It could be said that there is currently an excessive number of workers on site. Not only does it bring down the total efficiency, but also causes a lot of potential safety concerns. Our proposal 2 will be focused on increasing crew efficiency by only utilizing the amount of workers that are needed for the activity of the day. As stated before, the main activity is to place the prefabricated wall panels. Each cycle can be broken down into 2 stages, the transporting stage and the replacing stage. Reading of the crew balance chart, we see that the foreman and man 1 are mostly idle in the process, so it would be better off to let the foreman replace man 1 to reduce the amount of people on site. For the transporting stage, we need a worker to prepare the panels for lifting and a crane operator to move the panels into place. For the placing stage, we only need 2 workers to guide, level, bolt, and caulk the creases. We will assign the foreman to work on the placing stage because if he works on preparing the panels, then the crane will block him from overseeing the construction site. As a result, we can reduce the total amount of people on site to 4, 1 crane operator, foreman, and 2 workers. This will get the scheduled activities done at the same time while being more effective since the crew has less idle time as a whole.
One of the solutions we have come up for the problems we have observed. So smart placement of supplies is critical for maximizing productivity. Supplies should be placed in a fashion that they're easily accessible to the workers and can be moved to the site easily when they're needed. For the particular project we're studying, the wall panels are stacked far off the site. Because of this, the activity period for lifting the panels from where they're stored is lengthy. Not only is this a waste of time, it also renders the work environment quite hazardous due to all the swinging around of these heavy wall panels. This actually brings me to my second point. Part of the reason that the panels had to be placed so far from the site is that the crane is not appropriate for this particular project. As you can see from the schematic of the site, the crane has a large working radius relative to the size of the site. If the panels were placed any closer to where they need to be installed, the crane would have trouble lifting them up. The problem can be solved simply by having a smaller crane, which allows the panels to be placed much closer to where they need to be installed. This shows that contractors should be well prepared for having the right equipment for the job they're doing.
Hello, I'm Armando Sanchez,
Hi, I'm Pallavi Srivastav.
and we are in charge of the implementation plan and costs of the proposals to improve the productivity of the activity being observed.
For the first proposal, the foreman will contribute more effectively on site rather than purely supervising the laborers. We referenced the 2015 RS means and approximated the activity to precast lightweight concrete plank. The means gave us a daily output of 1,800 square foot, the labor cost of $1.24 per square feet, and a productivity of 0.027 hours per plank.
The crew consisted of a foreman, 3 laborers, and a crane operator. If we are eliminating the idle time of the foreman, the new labor cost will fall to $0.92 per square foot. This increase in productivity will save the project around $10 per panel.
This proposal is viable because not only are we increasing our productivity, but we're also decreasing the cost.
Our second proposal, we looked at eliminating a worker on the site and having the foreman compensate for his work. Looking at the labor utilization factor, we compared the productivity rating for the initial situation to the hypothesized one.
So for this proposal 2, the LEF increased from 0.5 to 0.625. This is a direct result of firing the laborer. If you assume that the foreman and the crane operator get paid around twice as much of what the laborer gets paid, the unit cost per square foot will decrease from around $1.24 per square foot to $1.06 per square foot, which is a good reduction in cost.
The third proposal, placing the material to a closer work area, will decrease the time of the activity. We looked at decreasing the working radius of the crane by using a smaller crane. We approximated a 10% decrease in labor hours to install the plank because of the decreased distance of the materials.
We will utilize a 7-ton hydraulic crane instead of a 12-ton hydraulic crane, and the assumed productivity will be 0.024 hours per plank compared to the original 0.27 hours per plank that we had. The lowest market price for a 12-ton crane is around $38,000. And the way to implement our third proposal is by utilizing a smaller crane, specifically a 7-ton crane, and the lowest market price for that is around $24,000, so that's a good decrease in cost as well.
Carlos Hoffman, and I'll be concluding our study for this project. Examined and put into consideration for implementation. Several factors were taken into account into how feasible each proposal was. Safety and complexity were two of the main factors that were made to compare each proposal. Proposal 1 is a straightforward solution that involves the foreman taking part in tasks where all crew members are participating to speed the time of that task. It's simple to implement and would maintain our safety standard by allowing the foreman to continue to supervise while only participating in specific tasks. Proposal 2 involves reducing our worker crew size by removing one of our laborers and having the foreman assume his responsibilities. Though the idea makes economical sense as it would save cost, while maintaining the same rate of work, it is not feasible in a practical sense. Worker crews are standardized, so removing one of the laborers would change the dynamic of each crew and could also affect worker morale. It could also cause an issue of liability if the foreman cannot accomplish the main task for which he is hired to do, which is to supervise and maintain safety standards. Proposal 3 requires replacing current equipment for smaller, more efficient equipment and placing materials strategically to reduce transportation time. Though a smaller crane could work much better in practice, it might not make economical sense. The current crane is one that is very commonly used, whereas the new crane proposed is not as commonly used. The amount of work the new crane can do is limited to smaller projects, so it can't be used as often. Therefore, availability and usability are two factors that hinder its practical use. To conclude, Proposal 1 is a simple but effective solution that can be easily implemented.